So my name is Dan Duffy. I am now the Chief of the Computational Information Science Technology Office. I'm going to talk about how we support the large-scale NASA climate and atmospheric simulations running on our systems and how we're basically supercomputing the Earth. So it really all starts, as you know, from NASA. It all starts with the observations, right? You got to take the observations, remote, in situ, wonderful, fleet of observations. You pass that into the model. These models are huge, right? Hundreds of thousands of lines of code running across, many systems, and then ultimately creating large-scale data sets for climate and weather. In addition to the observation data sets, some of these reanalysis data sets, some of these products that are created by these models, they're all free and open for data access and download. And you just have to make sure you know where they are and how to access them, and you can get them all you want. There are hundreds of petabytes of data out there that you can grab. So keep going. We'll get to the movies here pretty quick. We've been doing this for a long time with these high-performance computing environments. So here it shows just an evolution of our high-performance computing all the way up to this year's most recent upgrade. We're at 5 petaflops of compute, 5 times 10 to the 15th computations per second. That's a lot of computation. 100 petabytes of storage. You can store a Google playlist that's 260,000 years long without ever having to listen to the same song twice. It's pretty impressive. But what this has done is it's given the researchers an unprecedented ability to start from the lower resolutions and start to increase their resolutions and see new effects and introduce new physics, new chemistry into the models and get new simulations that they've never seen before. So that's what we're going to show you next. So let's get to the real stuff. We're going to start here. This is basically a simulation of an Icelandic Glow, and we're going to start from a low resolution, a 50-kilometer global resolution. And you can see it has the basic features of the Icelandic Glow here. Here's the front right there, but it's hard to tell the different type cloud features. When we go from 50 kilometers down to the current operational resolutions of 12 kilometers, you begin to see some of the better cloud features in there. You see what's happening in front of the front, what's happening behind here, but still it's hard to tell some of the specific clouds. And then we drop down to the highest resolutions that we're running right now. It's a 1.5 kilometer global resolution. This takes 1/3 of our system to run, and it takes a long time to run these things. We're running a few simulation days per day, generating tens of terabytes of data, and now we can really get down to seeing some of the specific cloud features and getting down into the cloud permitting scales of this model. You can still see the front right there. So the low resolution does a good job of the front. It does a good job of the gross features, but now we can really begin to see some of the clouds that are behind there, those stratocumulus clouds that are behind there. I think we have the high resolution next. So here's another picture of the same thing, but now we're just going to look at the 1.5 kilometer high resolution. You see that front coming off of the East Coast, going up there and creating that Icelandic Glow. So there's that front right there. You see some wonderful cumulus clouds right there, some good deep convection there. You see some marine layer out front. You see some thin clouds out there, and again, behind that front, when it comes back through, you'll see that stratocumulus surface features being developed with all the winds down there. So there, you can see these wonderful features behind the front there, and getting sucked up by the winds and created by the winds. So again, this is to date some of the highest resolution models run, US models run to date. 1.5 kilometer global resolution, 1 mile square global resolution. It's about 200 million grid points. Give you an idea. It also creates, a 4-day simulation creates 60 terabytes of data, which is a huge amount of data. If you think about it, in about 10 to 15 years, in the 2030 timescale, this will be the operational resolution of the weather models. These models will be run probably even every hour at this resolution for a 5 or 10-day simulation time. But we don't have the capability of doing that right now. Okay, we got 9 minutes. We'll keep going. Okay, in addition to looking at infrared temperature brightness, here we're going to look at simulated carbon dioxide in the atmosphere. So this is taking data from the OCO2 satellite and running it through a data simulation process with the model. Okay, so you're correcting the model as it goes along with your simulated observations. And what we're going to do here is we're going to turn this into a 3D visualization. This was shown last year at the AGU. We're going to show it again this year because it's so fantastic. But it also shows you the various concentrations of carbon dioxide. So what they do is, what the visualization does is it kind of takes out the middle area, right? The blue is the low, the red is the high, and the middle area is taken out. It also exaggerates the land features here in the atmosphere to give you a better idea how, how the carbon dioxide moves around the atmosphere. It moves around very, very fast. This is a simulation, the time scales from 2015, and it goes through the winter months into the summer months. Of course, the winter is where the carbon dioxide in the northern hemisphere is the highest concentration, And as you go into the spring, that's when it starts to get out of the greenery in the northern hemisphere begins to uptake that carbon out of the atmosphere. You can also see here the higher elevations there where it's low concentrations of carbon dioxide. It hasn't had a chance to mix up that high in that atmosphere yet. You can also see some diurnal cycles of carbon at the surface, some pulsing of the carbon at the surface, which is largely caused by some forest fires and things like that in Africa and South America. So some fantastic features here. You can see those pulsing at the surface. So again, we've exaggerated the elevation here. Now we're into the summer months in the northern hemisphere, and you can begin to see it clear up in the northern hemisphere as the northern hemisphere begins to green up and vegetation comes back and sequesters that carbon out of the atmosphere. These visualizations are online at the svs.gsfc.nasa.gov, so you can go and get these visualizations and impress your family over the holidays. So we have hyperwall stories right here. So let's go ahead and move to the hurricanes. So you saw a preview of this earlier today, and we're going to show you this. This is a very high resolution, a 6-kilometer downscaled model of the hurricane season from just a couple 3 months from this past year. Very active hurricane season. So what comes from the Global Modeling Simulation Office. This is the Goddard Earth Observing System model. And Dr. Bill Putman has created this. It's a replay. So you take the 12-kilometer forecast, and what he does is he basically replays down, spins up the model and replays down to 6 kilometers. So this is a 6-kilometer global grid. But we're not going to look at the moisture in the atmosphere. We're not going to look at the clouds or the infrared brightness temperature. What we're going to look at is aerosols, 3 different aerosols. We're going to look at carbon, dust, and sea salt. Okay, so this gives you a different view of hurricanes. Basically the column concentration of these aerosols in different views. You can see the various hurricanes pick up their skirt right there with huge amounts of sea salt in the atmosphere. You can see the dust coming off of Africa, reaching all the way across the Atlantic, getting into the Amazon basin, getting into the even on the East Coast. We have dust in our clean rooms at Goddard that we have to clean out that comes from Africa. See the fires out here in the Midwest and in the Upper West here. They come all the way across, and you see how much that smoke gets transported all the way across, all the way even over into Europe. So here comes Harvey. Harvey, you can see, has picked up a huge amounts of sea salt in the Gulf there. Harvey's going to do its thing. It's going to make landfall, which dissipate a bit, come back out. So you'll see that sea salt get rained out and dissipate. Harvey will come back out into the Gulf, pick up more sea salt, and hit land again. As you can see it come back out, it'll pick up some more sea salt, begin to form again there, and make landfall again. You'll see some other tropical disturbances turn into hurricanes over here off the west coast of Mexico. You see the convergence zone here as well. Here comes Irma. As you notice these hurricanes come off over there in the Atlantic, watch them bring up the cloud or the dust, and the dust particles begin to swirl around in the bands of the hurricane. And over time, those dust particles get rained out. They get wet deposition out of the bands of the hurricane, and it picks up a huge amounts of sea salt. There's Irma. Jose comes along right behind it. You begin to see Jose pull all that dust over from Africa as it comes, and again it gets rained out. Jose does a little loop there in the Atlantic. This is so great, I like to let this run for a while. I think we got time. Again, look at all this, the forest fires up here and how far that smoke reaches and how far it gets circulated through the atmosphere. Again, this is the GEOS 6-kilometer resolution. Here it becomes Maria right there, going over Puerto Rico, Lee behind it, and we'll finally get ultimately here at the end, we'll get to Ophelia in a second. There's Maria going right over Puerto Rico right there. You see some fires here. You can also see, if you look closely, again, the diurnal cycle of the fires. You can see some of that mixing at the surface layer. You can see the pulsing that occurs. Maria was huge. There's Lee again, picking up again a lot of that dust from Africa and pulling it all the way across all the way across the Atlantic. You can see how quickly the hurricanes begin to dissipate up into the North Atlantic there. And we're going to end here in just a second with Ophelia beginning to form. And you'll see Ophelia is one of those hurricanes that was very, very unique, right? So at the time of it It formed it was the farthest to the east and farthest north that a hurricane had ever formed at that time of year. There comes Nate. And you'll see the Ophelia start to come up and spin up right there. And what Ophelia does is it picks up a huge amounts of dust from Africa there. You'll see it begin to spin up the dust from Africa in its bands right there. And then there's some smoke from Portugal, a large amount of fires in Portugal. And Ophelia is going to pick up that smoke from Portugal and the dust from Africa, and it's going to transmit that all the way up through the UK into Ireland. It's going to go very, very fast through there. And if you take a look at some of the pictures of after Ophelia went through, there you see the dust go and the smoke go through Ireland there. If you see some of the pictures after Ophelia went through Ireland, you see a lot of those red sunsets. Those red sunsets, of course, caused by the smoke and the dust being picked up by the hurricane. So I think we have one more show of a very high resolution. So this is now, we were at 6 kilometer, now we're going down to 1.5 kilometer resolution. So again, we're kind of showing you the evolution from the computing side of how good these resolutions have gotten, all the way down to 1.5 kilometer resolution. Here again, we're looking at sulfates, sea salts, dust, and carbon. So here we've added sulfates and carbon in the atmosphere, and you can see some fantastic things. You see some nice convection here, and it brings up that from the Gulf Coast right into the Midwest. You see some convection that comes out here, some movement of the clouds coming off the coast here. You'll see some wonderful interactions with the islands out in Hawaii there. So again, this is about a 3 or 4 day simulation. It takes 30,000 computer cores, days of time to create this, and generates terabytes and terabytes of data. So, it almost takes as long to create the visualizations now as it does to actually calculate the model. That's how big these data sets are. So we're in the world of big data right now, but you get some fantastic visualizations out of it. So I'll let this run. I appreciate your attention. You guys have a great week. I'll do this show a couple times during the week, and let me know if you have any questions. My name is Dan Duffy. Thank you very much. Have a good day.